Welcome everybody, um, and welcome for the New Jersey people, and welcome to the Delaware and Philly people. And if there was somebody from further away, welcome also. Um, what? Let's see. How do I move this? Okay. Um, can you all see the screen? Eric, you can see my screen?
Yep, everybody should be able to see your screen.
Okay, great. Um, As I said, this is about developing and assessing learners' conceptual understanding of fractions. And I just chose fractions as a content area to talk about because virtually everybody ends up teaching it, and most teachers and most learners find it difficult. And, you know, one of those things, one of those topics that they either never got in school or never liked or never made too much sense out of. But what happens in adult ed is because everybody's really in a hurry to take the high school completion test or move on to the next step, there's a big um, emphasis on doing the procedures, um, which makes sense. But let's see, how do I move this?
If you, Linda, if you scroll down, you should see a little arrow key. Keep going down to the bottom of your screen. Yep, left-hand corner. There you
Use
go.
that?
Yep.
Okay. Okay. Um, all right. But as I'm sure most of you, if not all of you, know, that there are new college and career readiness standards based on the Common Core standards from K-12. And for math, they identify three instructional shifts, and one of them says that instruction should include equal measures of conceptual understanding, of key concepts, procedural skill, and fluency, as well as rigorous application of math in real-world contexts. Now, over the last few years, I think there's been a big push to help teachers, help learners think about using real-world contexts and applying the math that they're learning. It doesn't always happen really well, and there aren't a whole lot of really good materials. There's some, but at least people have been thinking about that. You know, how do I help learners take the math that they're learning in their class and apply it in everyday situations, in workplace situations for further education? So, but the part that we haven't been talking about very much is about the third part, the conceptual understanding of key concepts. And so I thought that's what we might focus on. Um, and so, as an example, you know, the NAEP is the National Assessment of Educational Progress, and sometimes it's called the nation's educational scorecard. You know, every couple of years they give this assessment to 8th graders or 13-year-olds as well as 4th graders and 11th graders. And a few years ago, the 13-year-olds were given the following item. Estimate the answer to 12/13 plus 7/8. And there were 4 options. And so take a second, consider which option you would choose. And then what happened was only 24% of the students answered correctly, which, by the way, is letter B, 2. And approximately equal numbers of students, a quarter of them chose 1, a quarter of them chose 19, and about a quarter of them chose 21. And if you look at the, you know, you can figure out where these errors came from. I imagine the 1 was, you know, people just thought you had 2 fractions, they're both less than 1, the answer is going to be about 1. 19, you may notice, is 12 plus 7, adding the numerators. 21 is adding the denominators. And the correct answer, B, should have been, well, 12/13 is pretty close to 1. It's almost 1. And 7/8 is pretty close to 1. So if you would add them together, your answer would most likely be very close to 2. it's to me, it what it says is that people are looking at for a procedure. Just here's some numbers, do something with them, without thinking about what do these numbers mean. How do I make sense of this? How do I understand this? Um, and I don't think I've never asked adult learners this question, and maybe they would do better than the eighth graders. But and maybe one of you might try this in with some adult learners and find out. Um, but I think it's really an example of the conceptual understanding piece. It's not a procedure. It's understanding what these numbers mean and what the implications are. So considering conceptual understanding, so what kind of definitions? What does this mean? What does it entail? So one definition that has been put out there, um, an integrated and functional grasp of mathematical ideas. So it's about the ideas, not about the procedures. And some of the ways to think about that might be making meaning, looking for relationships, interconnections between things, how to model, how the math can model, um, how the mathematics can be modeled, and how it can model situations, and using the word understanding. And if you look in the college and career readiness standards, you see this kind of language. Um, and as well, oh, I stuck this in. Um, One time an adult learner said to me, I know how to do this, just tell me if I have to multiply or divide, which of course was the part I wanted them to know. I mean, the calculator could do the multiplying and dividing, but the thinking part is, am I supposed to be multiplying? What is the situation? How does it make sense to me? How can I make sense of it? What does it mean to multiply? What does it mean to divide? How do these things connect? And so, and a lot of the workbooks just say multiply, these 400 examples, or divide every one of these examples, and there's not a lot of thinking. It's a procedure, and there's nothing wrong with procedures, from their early um, uh, request. It's a third of what you need to know, but you need to know how to apply it when the book doesn't say multiply. And to be able to do that, you really need to have the conceptual understanding of what do all these things mean. What does it mean to multiply? What does a fraction mean? Um, what does it really mean? Not just a numerator over a denominator and they're just numbers.
Linda, I think that's a good segue before we go on to, I know, your next part about thinking how we support learners on that. I mean, I think maybe we can open up the floor for a second in
Absolutely.
terms of, for those of you that are participating today, both your understanding of this idea of conceptual understanding and how do you see it playing out in your classroom? Do you hear students saying the same sort of thing that Linda has here, that I know how to do this, just tell me if I have to multiply or divide, or would make the same sort of mistakes that the younger students obviously were on that fraction sample? Do you see this playing out in your classroom, kind of the focus on the process and less of an ability to kind of grasp conceptually or holistically the concepts? And either, chime in by raising your hand and I can unmute you, or you can share some of your thoughts via the question area and then I can read them out loud.
Perfect.
And I think as people are, writing and thinking about this, although we're speaking about uh, math and fractions, this certainly goes across the board, right? This notion of what's the process versus really understanding the deeper concepts involved. You can think about students learning how to use maps in history class or something, and,
Mhm.
and going through it in a rote fashion as opposed to really understanding how maps are built and how maps represent the world, or in the language class and writing class, writing that 5 paragraph essay because that's what you've been told to do and taught to do, but not really sort of conceptually understanding what you're trying to accomplish by writing an essay.
I see Pamela has her hand up.
Yeah, hang on a second. So Jane, hang on a second. Let me say. So Jane shared exactly that some students will say, "Show me one, and I can do the page." Right. So walk me
Right.
through one, and I'll go through the page. And then Carol adds that most of the students know procedures, but when it's presented in a word problem, it's difficult for them to figure the answer. Right. As Linda just said, if you don't see the word multiplication there and you don't understand that that's what's being asked, then you're sort of stumped. All right, so I'm going to unmute Pam. So Pam, do you want to add something? I saw your hand up, Pam. Did you want to add something? No. Okay. Carol asks, many students, when we give them examples in real life, seem to get it more quickly. All right. So using contextualized examples.
Yeah.
Okay. All right. So I think, clearly we're hearing that this is not a unique experience, right? About students saying, I know how to do this. Just tell me if I have to multiply or divide.
And part of the problem is because students have so learned that the procedures are really what is important, or make that assumption, and
Hmm.
I think they've learned that from many different directions. First of all, it's standardized tests do a lot of procedures because they're really easy to assess,
Right.
right or wrong, as opposed to somebody's understanding. And so, sometimes I think there's pushback from learners who say, I don't care why, just show me how to do it.
Hmm.
Well, if you don't really know why, the next time it comes up, you won't know to do it.
Right.
And so, there's nothing wrong with learning the procedures. It's just not sufficient. It's not enough.
Right.
Um,
Okay. So one last thing, and maybe you can move on, Linda. Don says that students understand more if we use practical things. So three-quarters of a pizza plus five-sixths of a pizza. And oh, one last thing. Carol notes that students seem to be afraid to make mistakes too, and that. I think that's certainly a key issue.
it is a key issue, and I think as adult educators are so good at helping students feel safe, when they've had terrible experiences around school before. And part of what we need to help learners do is recognize that it's okay to make mistakes, that everybody makes mistakes, and the task is, what do you do when you get stuck? What do you do when you make a mistake? Do you just give up, or do you say, okay, this was a wrong path, or this led me to bump into a wall? What are the strategies I need to then make use of that information? Okay, I can't do it that way, so let me go back to the part that I did understand and I was able to do. Or strategies like, well, substitute smaller numbers and see if you can see how it works, and then deal with whatever numbers they are.
Hmm.
So helping learners develop strategies to address, the anxiety and the fear about it's wrong or it's right. No, this is what learning is about, and everybody, and as educators, to show people that you also make mistakes and you also have to figure out how to do the problem. It doesn't just drop into your head, and it won't just drop into their heads either. Um, and so helping people understand the problem solving process will help them recognize that making mistakes are great learning opportunities.
Hmm. I think that's a good segue to your next slide too, Linda.
Okay. Um, and so how do we help people develop this conceptual understanding? And as I said, I just chose fractions as something that most teachers have to deal with. But, and so these are specific to fractions, but they're not so specific. Um, Use multiple representations. A lot of our learners are very visual, and helping them see how things relate to each other can be very helpful. And I mean, the more I've taught math and the more I've taught the stuff that I knew, by looking at multiple representations of the content that I knew, I learned so much more or thought about things differently. So I think at all levels, um, and as educators, to have a bunch of alternative um, strategies to pull out when somebody's not understanding and when somebody needs to see it differently, and when is if we can have as many representations and ways of looking at things and ways of explaining things, we're better able to help learners. So, but I mean by multiple representations, and this stuff is really pushed in the college and career readiness standards, using number lines, using area models, particularly rectangular strips as well as other shapes. For fractions, using measurement. That's the place we use fractions the most, whether it's parts of a cup, parts of an inch, parts of a mile. We use fractions a lot in measuring, and many learners don't know how to measure. I was so surprised to find out people don't know how to use rulers and tape measures, or don't, I mean, they can stretch them, but how to read them, and that's all about fractions. So it's a great way for people to develop a real world useful skill at the same time as they're learning fractions. Using benchmarks, helping students, everybody knows what a half is, even though some people say, I want the bigger half, it really isn't quite right. But for the most part, people understand what a half is. Some understand what a fourth is. A lot of them don't, but that shouldn't be a big leap. But using those, so something is almost one whole, or almost, like 3/4 of an hour is between a half an hour and a whole hour. Just having the half, the whole, smaller numbers close. It's not closer to a whole hour than it is to a half an hour. And so using benchmarks, helping people develop those, and then forcing people to explain their reasoning. My students used to make fun of me because no matter what answer anybody came up with, I always asked why, or how do you know? And after a while, they would ask because they knew I would. And, because you never know if somebody ended up with the right answer for the wrong reason, ended up with the wrong answer just because of something careless. And so by asking people to explain, plus learners learn from other learners really maybe more easily than learning from a teacher, because lots of times a learner will have a way of explaining it, having more recently not understood it. So asking people to explain how did they do that, why did they do it that way, where did that number come from, is not challenging, but it's helping them justify their reasoning, kind of become aware of their reasoning. Sometimes people have said, I don't know how I did it, it just popped into my head. Well, that's ridiculous, it didn't. You figured it out, but you weren't very aware of what you were thinking. And you want to help them develop the language to talk about the mathematical reasoning. Any other comments about that?
Yeah, any other thoughts so around these sort of general conceptual things before? Carol notes as a resource that there's good videos on real life math at tv411.org.
Yes.
Yeah.
Yep. That is a good source.
Dawn notes that students explain to each other how they did something, and then they often have a completely different method from her. And she likes to see that their ideas are just as valid to answer questions correctly.
Yeah, I think that's the best. And actually, lots of times I've asked learners, can anybody come up with another way to do whatever it is? Because there's almost always multiple ways of solving a problem. And sometimes somebody will have come up with one way that makes way more sense to another student than, kind of the way that was presented. And it allows people to recognize, to help them see the connections. If we can do this strategy, if we can add up all these and get the right answer, if we can multiply those, if we can estimate and then subtract a little bit, I mean, all of those help people recognize that there's lots of paths to get there.
Mm-hmm.
Okay, so since we were going to talk about fractions, what are some of the concepts that are important for understanding fractions, and the reason these are important is not only for fractions, but this is good preparation for proportional reasoning and algebra, which usually come kind of after fractions. So, so I identified 4 concepts. Because if we're going to focus on conceptual understanding, we have to think, what are the concepts we want them to understand? And the concepts are generally larger than a specific task. So all the concepts I have are not about procedures, although they could be. You know, we could have, what does it mean to multiply fractions? You know, people assume that when you multiply it gets bigger, but not always with fractions. Sometimes it does, sometimes it doesn't. You know, so you can have those conversations. But I'm just focusing on what are fractions, just for our today's topic. And so I identified 4 important concepts. First is the magnitude, the size of fractions. Second is the fact that fractions are all about equal partitions, cutting up a whole so that all the pieces are exactly the same size. It's not the number of pieces, it's the fact that all of them are the same size. I mean, you know, it is the number of pieces too. But that's an important concept. Equivalent fractions. What does it mean when fractions are equivalent? And the final one is that the whole, W-H-O-L-E, matters, because fractions are parts of specific wholes. And if the whole, if, you know, 2/3 of an elephant is not the same as 2/3 of an inch. Just the idea of 2/3 by itself is not, it depends on 2/3 of what. And so the whole matters in that sense. So I have a couple of activities that some are specific to each of these 4, and the first one is a little more general. So this is a great activity. I've done this lots of times with teachers and with learners, where I put all of these fractions, and first I have to apologize. It's really hard to type fractions vertically, but when you're working with learners, it's way better than the diagonal slashed. Rather do it vertically, because then it's very clear what's a numerator, what's a denominator. And when you do them horizontally, like I did here, because it's so much easier to type that way, it's less obvious where the numerators are and where the denominators are. So I apologize for that. You know, this is one of those do as I say, not as I do things. And so I've just put each of these fractions on an index card and put a long string on the wall and put a 0 and a 1 and asked people to figure out where these fractions are on that number line. Create a place. And Carol Dan is not on, but I asked her to try this, and she did with some learners, and I was going to ask her to report back.
Oh, she's here with Mike.
Okay.
She's under Mike's name.
Okay. And I'm wondering if she could be unmuted. I'm
Yep.
not sure.
Yep.
And if she could describe what happened with her learners when she did this.
Okay, so Carol, you are now unmuted. Can you hear us? Carol, I have you at Michael's microphone, and I've unmuted you. Oh, maybe the microphone's not working.
Ah, too bad.
Linda, did you want people online to work on this for a second to see how quickly they could do it while we're trying to see? Or no? I just got a note saying that their mic doesn't seem to be working.
Okay, well, let me just report, and I know Carol has done this with learners earlier, with different numbers, and I just sent her these and asked her to do them. And I remember she told me that they didn't have much trouble with most of them until they hit the 4/9, and that one they had trouble with. But eventually they got it. And maybe, Carol, you could type in what kind of strategies did you see them using, both for the 4/9 to figure out where that went, but also for any of the others.
Okay.
Um,
Right. So, and while she's typing, the rest of us can maybe like visually kind of look at these numbers and see ourselves putting them on a number line.
Right. So, the task on the number line is figuring out where in the, first the relative place that everything goes, and where on the number line. Are they all bunched together? Um, and so people have to actually think about, what does 3/4 mean? I have to divide things into four, divide the space into four and count three of them.
Hmm.
For some of the other ones, I have to divide it into thirds or eighths or ninths. Um,
So Carol notes that they've both done the activity in their class, and for the 5/4, they did not get where to place the card until she extended the line past the whole number one.
uh-huh,
So I think creating the visual that it's a number line, right? That it's not just a segment between 0 and 1, which I'm
right,
not I'm not surprised by. If you don't have the line, students might think, well, where's this one going to fit? And
right,
they think the
and
parameters that you've given them are going to force them to put it between those two numbers.
right. And it's kind of, and you can have an extended line and just have the one um, at some point, and but nothing after that. So they have to imagine that some numbers, some fractions, are larger than one, and then estimate where along that it is.
Mhm.
Um,
I think that's going to be that's always an issue of how much do you want to create the opportunity for that sort of reflecting on the nature of the question itself. Do you want to
right,
have the number line there, or do you want a student to go, hey, wait a minute, this is more than one, so we need a string that's going to go out further than the one, right? And so that's great if that student says that, but not every student's going to be able to be able
right,
to argue against the nature of what they think the question is.
right. And I think, which is a great argument for asking learners to do this in pairs, say.
Hmm.
So, it's not one person who is stuck with a particular number, if you deal these out to everybody. Um, or, and they have an informal way of saying, well, wait a second, I can't figure out where this goes because it has to be more than one, because this is 4/4, so what am I going to do with the fifth one? Um, and to have that conversation. Um, and I know um, some of the other ones, like 4/9 as an example, once somebody has a half there, they might say, well, half of, if it's ninths, 4.5 ninths would be a half,
Right.
if they happen to think that way. Or they could divide the space into approximately 9 pieces, and they have to be equal pieces, and we'll talk about that in another activity. But this
That's
is,
what I was gonna
go
say.
ahead.
That's what Carol or Mike just added, saying that for the 4/9, that's what they did in their classroom. They do a rectangle and divided that rectangle into ninths, and then talked about half of nine, and so then drew a dotted line between the fourth and the fifth part of the ninths.
Nice.
Okay.
Okay. So to be
Jesse wonders, would it help to change the question to students to something like, put these in order from the least to the greatest, or should the focus be on how it is part of one?
Well, I actually have another activity with comparing two numbers, which one is larger. Um, and I think you could certainly do that with this activity. Um, Either way.
And I also think that I think the point that Jesse's raising is that uh, when you're giving instruction to make sure that you're changing the nature of your vocabulary over the course of your instruction, right? So that the students hear the concept phrased and presented several different ways. So they're not looking for one particular way of saying it, right? Or they're not looking for just that word multiply. So if they're hearing something like least to greatest or part of one, they're getting the concepts from a couple of different perspectives, and that gives them the kinds of strategy and flexibility that they really need to understand the concept. And
Yep.
Carol adds Mike adds one of his strategies was to focus on some of the benchmark fractions such as 1/4, 1/2, and 3/4, and then they were able to estimate where many of the other fractions went on the line, right? Using those kind of main fractions as kind of anchors, and then working around those.
Right. So the point is there is no computation here to speak of, but it's really paying attention to what does 1/6 mean. It means the space between 0 and 1 is divided into 6 equal pieces, whether it's on a line or a rectangle, and I have some pictures of those. Um, and one of them, or 3/4. It means it's divided into fourths, 1/4, 1/4, 1/4, 1/4, and you have three of them. It's like 3/1/4 or 2/1/3. So lots of different ways to think about it, and to think about what do these particular numbers mean when it says 3/4? What does that mean? Because the 3 and the 4 have totally different meanings.
Right.
Um, okay, let me go to the
Yeah.
next one. So here it's about comparing fraction size. So just two at a time, because having 10 of them is a lot. Um, which fraction is larger, and why do you think so? Um, how could you explain how you reasoned about it? Don't use a procedure such as cross-multiplying or finding common denominators. Just think about what do the numbers actually mean and show. So we have 3/8 or 3/5. So, and to come up with as many different ways to compare them as possible. So does anybody have some idea how you would decide 3/8 or 3/5? Which one is larger and why?
And people can write in with the question, write in with your thoughts, or
Right.
raise your hand. And I think this goes back to your point about modeling for students, right? As many different ways of thinking about things as possible.
Yeah.
And
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 so,
also, and I think the instruction here good about, like, not cross multiplying or finding common denominators. So not going immediately into that sort of rote procedure that you've taught, but to stop and think conceptually what it is that those numbers really represent
right,
before you start to jump into the routine.
because the cross multiplying, people don't understand what they're doing.
Right.
They just, so once people learn how to cross multiply, when they have to add fractions, they cross multiply.
Mhm.
When they have to multiply fractions, they cross multiply. Just
S-
because you see two fractions next to each other, cross multiply,
Right.
it gives you something to do. And there's no need to do that
Right.
for these.
So Julie notes that to find decimal equivalents,
Okay, that's
and then you
one way to do it.
and then you can and compare it to money. Jane notes, for example, that 3 is more than half of 5, right? So that
Nice.
3/5 is larger.
And so
Uh,
that's using a benchmark. So 3/5 is larger than a half, whereas 3/8, 4/8 would be a half, so 3/8 is less than a half.
right,
So
and then Carol comes from the other direction and says that 3/5 is larger because 5 equal parts are larger than 8 equal parts, right?
exactly. So if you have three larger pieces, it's going to be bigger, more than three smaller pieces. Exactly.
Right? And Don was thinking the same thing, and Angela was thinking the same thing as well, in terms of giving that sort of explanation.
So something as simple as that, as this task, can be very rich in conversations about what do these mean and what are different ways of thinking about them. And and so here on the next slide, here are some possible strategies for comparing fractions. So you could have placed them both on a number line, like the problem before. Um, because they had the same numerator, or the same denominator. You're reasoning about sizes of pieces, or if they have the same denominator, how the number of pieces of the same size. Here they had the same numerator. They both were 3, so somebody reasoned about the size of the pieces. Somebody compared them to benchmarks, such as greater or less than a half. Distance, and thinking about distance, which is kind of the same thing, benchmarks, farther down, closer to the other end. And then visual models such as rectangles, circles, or shapes. When we teach fractions, often the only shape students see is a pizza. And it's the least useful because you can't multiply slices of pizza. I mean, you can say 4 of them, but you can't easily understand what 2/3 of a quarter of a pizza is. You could cut it up, but you can't cut it very nicely because it's a wedge. Rectangles are way easier, and so instead of round pizzas, we have to think Sicilian pizza.
Right.
But the idea is that there should always be a rationale and an explanation that students provide for how they figure things out, or how you figure it out. Because that's where it's not the answer that matters. It's how you reasoned it out. Any questions about this?
I think given the time, Linda, I think maybe we should move on to the next
Okay.
one. Okay.
So here we have equal partition, and these are, notice that it's the same numbers, 2/3 or 3/2, 5/6 or 6/5, 5/7 or 7/5. And so here it's really about focusing on what do these denominators mean. It's about equally partitioning something. And the first one is partitioned into thirds, 2/3. The second one is partitioned into 3/2. So I have an example of, here's 2/3 and here's 3/2. And you can see how the rectangles really are easy to look at, to see parts, way easier than pizzas. So here, looking at the difference between 2/3 and 3/2, it's about the size of the pieces. If they're thirds, they're smaller than halves, and you have 2/3 and you have 3/2. It's quite different. And the same thing for 5/6. Whoops. How do I go back? 5/6, 6/5. Same idea. And so I have a similar task, in a sense, about partitioning. And there are 3 squares here. And I wanted to ask you, is the first one divided into fourths? Is the second one? Is the third one? Which ones do you think are divided into fourths? And if anybody wants to raise a hand or
Okay.
type an answer. They're all divided into 4 pieces.
Angela, I think 1 and 3.
Okay, can she explain why?
Yeah, can you explain why, Angela? Maybe to type in your explanation of why. Somebody else says all of them. Somebody else says top and the bottom. So we have 2 competing answers right here.
Okay.
We've got 1 and 3.
And 1, 2, and 3.
And 1, 2, and 3. Okay.
Okay, is somebody typing
Some people are, let's see,
an explanation? Or
1 and 3 and 1 and 3 are
the lead?
the lead. Yes, 1 and 3 and 1 and 3 are coming in. So one person's explanation is just looking.
Okay.
Okay.
So the first one, let's take a look at the first one. I think everybody agreed was divided into fourths. It's, the diagonals instead of the vertical and horizontal, which is usually the way these things look. But each one of those pieces is exactly the same size. And so that counts as fourths because the pieces have to be exactly the same size. The second one has four pieces, certainly, but the problem is they're not all the same size. Um, on the bottom, the middle piece is twice the size of each of the side ones, and the horizontal piece at the top is also larger than the side ones. Um, so while they're four pieces very nicely, that's not divided into fourths because they all have to be equal size. And the bottom, I thought that was going to snag people, but apparently not. um, because, all the lines aren't straight. And, and you can see that the pieces fit together. You could imagine that they actually are all four equal size. So it's just an activity like this is just a way to have people talk about the fact that all four pieces or however many pieces have to be the same size.
And I think it's nice to see this drawn on graph paper as opposed to using manipulators like Cuisenaire rods, which are great things. But
Uh-huh.
this gives you, I think, a little bit more flexibility in terms of how you're going to set the visuals up than say Cuisenaire rods would.
Yeah, yeah. And it's also worked better
Uh-huh.
on a PowerPoint.
Yeah,
But
yeah.
um, but you're right. And it also gives you the benefit, especially in the third one, you can't really see the graph paper very well, but if you could, and I did do it on graph paper for reasons including I could draw squares, um, even though when I copied them they're a little slanty, um, but that you could actually see where the lines are and how much is above the line, how much is below the line for the third one.
Hmm.
And it also gives you very clear visual um, cues about the second one, about how the middle section on the bottom of the second one has more squares in it than each of the side ones.
And this is certainly something that you could encourage students to do for each other, right? That once they
Right.
understand how this works, they could quiz each other and challenge each other by drawing things that are
Or
equal
aren't.
fractions
Right.
or aren't equal fractions, and
Right.
then have the person explain why it is or it isn't.
Yeah, that's a great idea. Any other
Any other
comments?
thoughts about these equal partition tasks on the graph paper? It's a great use of graph paper.
Okay, so here we're talking about equivalent fractions. And so rather than doing cross multiplying or but to draw something that confirms your thinking. So kind of decide if any of them are equivalent and then prove it with a drawing. And so just in the interest of time, I have all three of these drawn actually. So, so here using a number line, using the same number line for both, it goes up to 1, 0. So 3/4 was dividing the the 1 inch, one whatever it is, into four pieces, 1, 2, 3, 4, and then also dividing the same space, the same 0 to 1, into 8 equal pieces, and seeing that 3/4 is in exactly the same place as 6/8. Rulers are great, or tape measures are great for doing all this stuff. You can find, I was in a Home Goods and they give away tape measures, like paper tape measures, and they're in quarters. Usually things are in sixteenths or something. They're in quarters, which is great to bring into a class. I recommend. Um, and then you could divide it up into eighths as well. Another way of visualizing the 3/4 and the 6/8 is with rectangles, taking the same size rectangle, pardon my ugly drawings, and dividing it into 3/4, dividing it into eighths, and counting 6 of them, and showing that they take up the same amount of space. And of course, then you can have a conversation about how every fourth is divided into 2 parts to make eighths, because 4 times 2 is 8. You get twice as many. So here we have 2/3 and 4/5. You can see why 4/5 is not equivalent to 2/3. When you divide it up into fifths and divide it up into thirds, it's a different amount, different size pieces. And even though some people might argue, some learners, hopefully not teachers, that each one is missing one piece, so therefore they're equivalent. 2/3 is one missing one piece, a third, and 4/5 is 4 out of 5. There's one piece missing, so they're equivalent. They're each missing one piece. Problem is the pieces are really different sizes.
It'd be also fun, I think, as part of this, Linda, to have students go from these drawings and then figure out what the whole is, right? So to think, okay, well, here's 2/3 of a semi truck versus 2/3 of a sandwich, and so to kind of to go back again, to kind of expand it again, to
Right.
increase that
Right.
focus on that
To,
point.
to not have the blank piece and just say, like, if for the 2/3, you had the 2 pink things and say, this is 2/3, what would be the whole thing?
Right.
So if these are 2/3, that means you need one more third. It would have to be the same size as each of the pink thirds, and you can get a whole.
Right.
Which is what happens when you do percent. Like, 75 is, or I'll use easy, 30 is 25% of what?
Right.
And this
Right.
is the similar kind of thing.
Pam, you had your hand up. Did you want to add something? No? Okay.
Okay, and then the last one, I thought is 4/6 equivalent to 6/9? Now these numbers aren't so nice. You can't just double the numerator and double the denominator or something. So, but if you show them on number lines, and of course the task is that the ones have to be and the zeros have to be in the same place. It's got to be the same distance from 0 to 1. And the top line is divided into 6, bottom line is divided into 9ths, and you can see that they come out in the same place. You have to be sort of neat about dividing your lines up. But then, once you've done this, you can have the conversation about, yes, this is lined up, but we had 2 other numbers, 2 other slash marks were lined up as well. And if we draw lines through all of the numbers that are lined up, we see that, and that's where the 1/3, 2/3, where 6/9 and 4/6 both can be reduced to 2/3. And you can see the relationship, how these things make sense, where it comes from. Now this is a little more sophisticated. I wouldn't start with this. But after people have been doing fractions for a while and they're reducing fractions, and this is kind of the explanation for why does this work visually, what is happening here, and why are 4/6 and 6/9 equivalent? Well, in effect, they both can be reduced to 2/3, but where do you see that? And here you can see it. Any thoughts or comments?
Carol says she likes that. Angela says she likes it. And I think this always points to the fact that technology is nice. Whiteboards are nice. All these things are nice, but so is a piece of paper and a pen, and a conceptual understanding of what it is that you're trying to get across.
Right, and things like rulers and tape measures are so useful for this. Um, and it's so easy then to see why 3/4 of an inch is the same thing as 6/8 of an inch, and the same thing as 12/16 of an inch. They're all the same line.
Yep.
They're all, it depends on which hash marks you're paying attention to, and then people know how to measure things as well. And so then the last question is, are any of these equivalent, and why or why not? And what I mean by equivalent is, or what I'm pointing to is the yellow shaded areas.
Ah, I see. I'll give people a little bit more time to respond this time before I start reading out the answers.
Okay.
All right, any other answers coming in? There's one that says there's two competing responses. There's a couple of responses that say yes, that they're all the same. And then there's another set of responses that say number one and number two.
And in a class, I would
Oh, and then
ask,
there's a last minute one that says the second one and the last one.
okay. And so the reason I put this up is because there is something to talk about here, I think. Um, and just in the interest of time, if we were all sitting together, I'd have people make arguments for all of these alternatives. Um, I would say that the 2/3 on the left and the 6/9 in the center are equivalent because they really cover the exact same amount of the same size rectangle. The one all the way to the right is also 6/9, but the whole the whole rectangle is not equal, is not the same size as the others. So while one could say this is 2/3 and 6/9 and another 6/9, it's 6/9 of something else. And so I would say just the first two are equivalent because the other one, the whole, is something different. But this is why I put this in, because I think it's worthy of talking about and arguing about and um, and paying attention to in terms of what's the concept that matters. Is the size of the pieces? Well, the size of the pieces matter. The whole matters more, and the relative number of pieces over the size of the pieces, like 6/9, would be equivalent to 2/3 on the first two rectangles to the left. 6/9 is the same as 6/9, but the holes aren't the same. So it would be one of those 6/9 of an inch and 6/9 of an elephant. It just means something different. But this is, an issue. We, most of the time, don't pay any attention to it. And we just have naked arithmetic, and there's an underlying assumption that they're of equal things. But we don't say that very often. But the assumption is there, because otherwise, how could you add a half and a half and get a whole? The halves have to be halves of the same size thing, or the same thing. And so I'm glad there were different perspectives, because that would make a good conversation, and it would make a good conversation in a class.
Mhm.
And so the final slide I have, and then I do want to give people a chance to talk, is just a summary slide. So how do you know when a learner has a conceptual understanding of fractions? And some of the aspects of that is they understand what numerators and denominators represent. They're not just numbers. They have different meanings. And one is about size and one is about quantity. You know, how many. One is about what size are they. They can explain and reason about fractions using benchmarks, sizes of pieces, quantities of pieces, like what we just did. Can draw sketches picturing fractions, and it doesn't have to be lovely, but it kind of explains what they're thinking. Can find equivalent forms of a fraction, show them visually, can order fractions, recognizes that fractions can be equivalent only if the wholes are the same. And so, you know, I'm looking at these kinds of activities as classroom activities that generate discussion, and people have to explain their reasoning. But then these are also formative assessment opportunities for the teacher to have a sense of what are people really understanding and what do they not understand, um, which goes beyond do people know times tables and, you know, the usual stuff we deal with, but actually focusing on the understanding part because there's no computation or very little computation. So I would like if anybody has some comments or thoughts or ideas of what you do in class. And if people want to email me, I have these activities pretty much the same. I change little small things on a Word document that I'm happy to send out. And of course, we can send out the PowerPoint as well. But
Yeah,
um,
we'll send out the PowerPoint. We'll also send out the certificate of participation for people, and it will be uploaded to YouTube. There was a question from Meg, not to directly ask your question, but Meg asked a question about ESL and how would you say these concepts are applicable to ESL? And as a former ESL teacher myself, one of the things that I would say is that sort of bring this to the class when you're thinking about the nature of language use, right? So even thinking about a simple word like yes, so if you learn yes just in kind of in a rote conversational way, you don't necessarily understand all the nuances of how we say the word yes and how we understand what we mean when we say yes. And so one of the things that I tried to do when I was working with my students was to not simply say, here's person A, here's person B, but as much as possible think about kind of the nature of language itself. Um, and that sounds really complicated for an ESL class, but I did a lot of work like that with my students to think about when do you say when do you strategically use certain words, and to use them successfully, you have to understand how those work.
and as somebody who has never taught ESL but been a language learner in an ESL kind of program out of the country, um, the fact that this relies a lot on visual can help people express something when they don't have the language. And, you know, to help people understand some of the math. You know, I mean, a big thing that happens when people come to this country is they're used to using metric, which makes so much more sense than all the fractions we use. Just going to the grocery store and asking for a quarter of a pound of cheese. Um, and so helping people understand the fractions also gives them a little bit of understanding of our measurement systems here.
hmm The other thing that came right to mind was I think this issue of understanding what the whole is and understanding the context of where the fractions are. Certainly, if you're thinking in ESL about a dialogue or if you're thinking about conversational routines that we have, context really matters, right? So you don't talk to your boss the same way that you talk to your friend, right? And you don't talk to a nice boss the same way you talk to a mean boss. And so you can have those conversations about what kind of boss it is and how do you choose your language when you have a mean boss as opposed to a good boss. Um, Michael says that they found some of these activities from ANI have been very useful, and the students do seem to have more of a conceptual understanding of the concepts. ANI is Adult Numeracy Initiative. Is that what ANI
Yeah,
stands for?
yeah.
Okay.
And the folks from Camden are doing A&I with folks from Delaware.
Okay. Other thoughts that people have, either specifically about fractions and math, or how to kind of take these concepts to broader. Angela says she finds that the pizza model doesn't seem to work that well for understanding fractions, right? I think it, as Linda said, it's commonly used, but it's not necessarily the most productive way to go about it. Certainly not the round pie. Maybe the Sicilian
Right.
pie is a way that people can explore. There's a real missing opportunity for product placement, right? We can maybe get like
Yes, yes.
the Pop Tart people to underwrite some adult numeracy curriculum if we encourage people to use
I
Pop
mean,
Tarts as the fraction
certainly,
visualizers.
certainly plain Hershey bars, they
Right,
divide into tenths,
right.
and they work real well.
We can wait another second, but me wrap up. So thanks again, Linda, for I think another interesting and sort of insightful look at mathematics and the way that we can help our students understand these larger concepts.
And thank you all for participating in your good questions and comments and figuring out stuff.
Yep. Right, so happy holidays to everybody. Be safe and joyous, and we'll see you in the new year, some point with the next set of webinars, probably starting early in February. We probably won't be doing any in January because we'll be setting them up and getting all the logistics set up. But probably starting in early February, we'll start to have our series, and then hopefully by mid-January, we'll send out the announcement of what the series is going to be. All right, so take care, everybody. Thanks again, Linda.
Oh,
And
you're welcome. Thank you.
I'll see everybody else online sometime.